So hi, Pete Shersby from Make or Repair, and today we are going to have a bit of a battle of the batteries. These are some of the batteries that have gone into our recycling bin over the last month or so, and as you see there's quite a lot. Now I'm not so worried about these big ones because those are out of torches and burglar alarms and things, and actually there's a few more. These, however, there's an awful lot of, and the reason for that is that I use these in my microphone that I use for these broadcasts. So this is a wireless microphone, clips onto my lapel. There's a little microphone clips on my lapel, of course, on my t-shirt, and yeah, I seem to go through those like water. So these are Duracell Industrial, which are the same as Duracell Ultra, which would be the brand you'd buy in a shop, and they're basically the same. They're just a little bit cheaper in bulk. But I've moved away from these a little bit because these Duracells and their industrial counterpart are absolutely buggers for leaking, particularly in things like remote controls and that sort of stuff. So I switched across to Energizer Ultimate, which are lithium batteries, primarily to assist with the leakage problem. So these are in my remote controls and in my PIR sensors and all sorts of things, the handsets on my VR controllers, and in some things they seem to last really well. One of the reasons they don't leak is because in the top, I'm not sure if that's particularly visible, but hopefully it is, you will see there are pressure relief holes in there, and there's a PTC in the top of this so that it doesn't get damaged by overcurrent and all that sort of thing. So yeah, nice little battery, very expensive though. So having gone through about 20 of these, I decided last time that I would stock up on some of a cheaper variety, and I knew I was taking a bit of a risk, but these are nice power lithiums, 3 amp hours supposedly, which is about the same capacity as the Energizer, and I would use those for my microphone. And you know, I'm kind of underwhelmed, I think. To be honest, the Energizers didn't do that well in there, and these didn't do that well, and I don't know whether I should abandon these this time because I need to put in a new order, or whether I should pay for the more expensive one. So I decided I would do a test and find out. So I'm actually just going to drain 2 of these batteries and measure what the actual current is, and so I'm going to drain them at 250 milliamps, which is quite a large drain for a battery. But for a lithium battery, one of the points with it is that you can deliver a large amount of current, much better than you can with an alkaline battery. So that's what I'm going to test them at, 250 milliamps, and one of the reasons for doing that is because that's the value they use in the Energizer Producer Handbook. And they illustrate it at 250 milliamps in that handbook, so that's what I'm going to use for my test. So I'm basically going to plug it in to this guy up here, which is my load, programmable DC load, and I can program this to draw out 250 milliamps, and it will monitor the voltage over time as that gradually decreases, and it will measure the milliamp hours that are available in the battery until it's exhausted, and I'm going to set an exhaustion point of 1.2 volts. When it hits that, it is exhausted. But before we move on too far, I'm actually just going to do a little thing with this meter. Yeah, that should be good. I'm just going to put that on volts. So if you haven't used lithium batteries before, there'll be something you might not be aware of. So here it is on its volts. This is a new battery. There you go. Basically, a lithium battery is 1.8 volts without a load. So yeah, so if you get a lithium battery, I don't know what this one's going to read. It's a dead one. Okay, 1.39, so you know that was dead anyway, but I'll try just another one. But if you get a lithium battery and it reads 1.62 volts, You might think, well, that's absolutely perfectly all right. It isn't. That is a dead battery. I mean, you could plug that in and you might get like 10 minutes out of it or something like that. But essentially, it's dead. It should be 1.8 volts, no load. As soon as you turn on your electronic device, it drops very rapidly to 1.5 volts-ish. So that's the characteristic of the lithium batteries. And it will then tend to stay fairly high for a lot of its, or should stay fairly high for a lot of its usage. Which, if your, let's say for example, your battery meter in your camera or whatever is calibrated for alkaline batteries, which have a more gradual discharge, then it will be fooled into thinking that you're fully charged. And one of the things that was happening with my microphone was that that it would show full charge, and then in the middle of a recording just cut out because the battery was dead. So yeah, there's a different characteristic for a lithium battery, but we'll see that as we test it. Okay then, so before I just look at this, one of the other things that I wanted to say was, one of the having had the fun of replacing batteries endlessly, I have eventually switched to using an external battery bank to power the transmitter. So this has been going about a week and a half, maybe 2 weeks now, and is at 53%. One of the good things is that this actually surprisingly takes a lot of current in standby. When this goes into standby, it cuts the power completely, so it lasts a lot longer, so I'm happy with that. But I do actually, as part of, I am reviewing this at the moment, and I do want to measure its performance. So this was another motivation for doing this battery comparison. So I have connected up a battery to the DC load, and I don't want to run it directly from the DC load. I'm actually going to operate it from the computer, and we can see here the software that Tenma provide for this. This is a 72-13210 programmable DC load. It's 120 volts DC, 30 amps, 300 watts is what we can actually do with it. We're going nowhere near those, of course. And I'll just have a look at a couple of little bits and pieces within that. So first of all, we can drive it manually using this section up here. We can set a constant voltage, constant current, constant resistance, or constant wattage power, and just type in some numbers there, and then we can turn on the, it says output, but strictly it's input, on down here, and it will just apply that load, and that's fine. And that's how I use it most of the time, and I don't bother with the software for that, of course. I just use it on the benchtop. Down here we've got a graph of the voltage and another graph of the current. We can change the voltage scales a little bit, but they're set for this particular test that's running at the moment. In the center section is a little bit where we can put a sequence of tests. So this one says I want constant voltage 4 volts for 2 seconds, and I want to switch to constant current 1 amp for 2 seconds, then resistance 1 ohm for 2 seconds, and so on. And we can configure that down here as well. How many of the test points do we want to use, how many cycles, etc, etc, and hit start, and it will run through that sequence. So you might use that, for example, for doing things like testing steps in current. So we could see how responsive, for example, our battery is to a sudden change in current demand. This section at the bottom here is just about configuring the machine. You can put some limits in, so you can't give it too much voltage, for example. On the right hand side, we've got the battery test section, which is what is running at the moment. So you can see battery stop is lit up at the bottom there. It is counting that it's done 811 seconds or so. And oh, that was quite handy. And it literally just reaches the setting value. And so it's set to terminate at 1.19 volts. So when the battery discharged to 1.19 volts, bang, it would switch off the test and finish it. So we can see on the graphs on the left that suddenly the data has spiked, the voltage has spiked as we've taken the load off, and the current has dropped to 0 because we're no longer running the test. It ran for 811 seconds, and it had a capacity in that battery of 56 milliamp hours. So this was actually a battery that had been previously discharged, left overnight to pick up a little bit of charge, and that's how much we actually got out of it the next day. So we could have, you know, made an emergency phone call or something like that, or taken one picture with our camera, something like that. Nothing very much, but yeah, in a push, it's there. And this is a lithium battery, but alkaline batteries do the same thing. So there we go. Of course, we've just got to read out at the top of what's going on. There's 1.35, the battery is recovering voltage. Now it's no longer under load. So we are going to set up the test exactly the same settings as this for our lithium batteries. And we're going to discharge at 0.25 amps, which is 250 milliamps. We're going to terminate at 1.19 volts. And that's so we've got graph data that crosses the 1.2 volt line. So I'm saying the battery is definitely dead at 1.2 volts. Its discharge capacity is 3 amp hours, which is correct for both batteries, and we're going to discharge up to 50,000 seconds. So if we get to 50,000 seconds and we're not down to 1.2 volts yet, then the test will terminate anyway. And as we can see on the screen, it will show how many seconds the test has run for and its capacity. If I switch to a folder now, try and find the right folder. I'm just going to turn the data off. Then we can see it actually outputs a huge long file with all of those voltages in it. So we can see we started the test at 1.7 volts. This line here is where we turned on the load. So we've got 1.7 volts, but no current. This is where the load came on from the battery. Thank you very much. We loaded the battery and it fell all the way down. And here we see 1.2011 volts, 1.996 volts, and just after this one, 1.191, the next reading would have been below 1.190 volts, which is my cutoff for this test. So at that point it disconnected the load and we can see the battery starting to recover immediately just there. Now we could calculate the internal resistance of the battery at that moment by subtracting 1.191 from 1.3275. So that's the recovery at the moment we disconnected the load. So it literally leapt up that little bit. So that would be pretty much all internal resistance of the battery. And yeah, we take the difference between those, divide by 0.25, and that will give us the resistance. A good battery would have a resistance of about 0.08 to 0.15 ohms, something in that region. This will be a lot bigger than that. Okay, so there we go. That's the setup for the battery. This was just a battery to run the process to make sure that everything was set up and working for the test on the battery bank. I have run the test on both of the lithium batteries now, and I did have some difficulty with some data logging, so there's a couple of weird bits in the graph, but I'll show you that in a second. So on the left hand side here, the first few bits of data are okay, and then we got a little bit iffy here, and that's because it wasn't logging data correctly, and so I had to observe it periodically. Now the data smoothed out about here after it's been running 2.8 hours, because just here I was working at the computer screen and I just set a reminder to go and take a reading every 15 minutes. So it would ping and I would go and take a reading, and yeah, that's how I spent my evening. That's a bit sad, isn't it, really? But anyway, the long and short is that the top line is the Energizer and the bottom line is the nice power. Now both of these are supposedly 3000 milliamp hour batteries. They both started at about 1.8 volts when I plugged them in, and they fell as soon as a load was applied. And on the left hand side we can see that the Energizer dropped to 1.48 volts as soon as I applied the load. The nice power dropped to 1.356. Let's look at the Energizer first. Now this matches fairly well the data sheet from Energizer. So this is a very useful document if you're interested in batteries and powering things by batteries. Good thing to look at. Energizer do a lot of these. So these are their handbooks and application manuals. So yeah, absolutely definitely worth going to the site to these. I will put the link in down below, not just for this, but for many of their other types of battery as well. And that's very, even if you're using an unknown battery, useful to understand how that battery works. So these are lithium iron disulfide batteries. So they're not lithium iron ION, which would be a 3-volt battery. It depends upon the presence of this iron disulfide in order to get the 1.5 volts. Lots and lots of useful information about how they're constructed, what their characteristics are. There we go, nice picture of how they're constructed, and the fact that they actually use lithium metal in it, not lithium ions. And interestingly here, there is a vent ball in the top, which I think I pointed out when I showed you the picture of the thing I was going to test. There is also the PTC in there, which is a positive temperature coefficient little resistor. So it will start at a fraction of an ohm, and let's say 10 milliohms or something like that. And if it heats up because there's a lot of current being drawn, the resistance will rise and essentially cut off the current, so that this battery doesn't overheat and catch fire or explode. So I'm guessing in a cheaper version you may well not have that safety device. Anyway, let's scroll down a little bit. All sorts of stuff about the thing. So here's the now this is why I ran at 250 milliamps, because this graph is at 250 milliamps, and we can see basically there you have plotted this graph over a number of different temperatures, and this one here, 21 degrees, is round about what we are dealing with. I think my lab was about 20 degrees at the time. So yeah, I'll give you links to this. There's an interesting thing on continuous discharge here. So on the left hand side we've got alkaline is red and lithium is blue. So if we look at an alkaline versus lithium at normal room temperature, we can see that the lithium only has about a 10% capacity improvement on the alkaline, and that's at 25 milliamps, which is not a huge amount of drain. It's just a small simple device. If we switch to a high drain device, so like a big powerful torch or something like that, then the lithium has significantly greater capacity than the alkaline. So yeah, interesting graphs and interesting comments on temperature, and lithium generally outperforms alkaline across a wider temperature range. So anyway, there we go. That's that data sheet, or handbook, I should perhaps say. They do a data sheet, but it's not as interesting. But yeah, I'll put all the links in down below to the Energizer site and the data and handbooks and things that you can get from there. So yeah, so our Energizer runs across just below 1.5 volts for best part of 3.5 hours before we start to see it tail off. Now this looks like a straight line sloping down here, but it's not really straight. It's a little bit curvy. It just doesn't really show up on the graph. Continues through, and we eventually get down to it has expended 3 amp hours at, what point is that? 12 hours and 25 minutes. Sorry, 12 hours and 15 minutes, I should say. We've reached that, and its voltage is down to just below 1.3, so it's 1.2288. So most equipment, not necessarily some things that just rely on a little bit higher power, but a lot of equipment would still be running at that point. So you're getting a full set of power out of this Energizer. If we look at the nice power underneath it, not quite so good, I'm afraid. So pretty much straight away we're down into the 1.35 volt region and below, and actually dropping after, where are we now? So I've got a dotted line across here because after 4 hours 15 minutes we're at the same point voltage wise as the Energizer was after 12 hours 15 minutes. So, you know, that's not really very good news. This battery is showing up on a lot of meters at this point as being pretty much exhausted, and it is pretty much exhausted in fact, and it's only done 1 amp hour. So the voltage on the Energizer holds up an awful lot better, which would imply that it has far better internal resistance than the nice power. Okay, so where does the nice power finally run out of steam? Just over 2000 milliamps. So yeah, that's not very good news really. So it's rated as 3000 milliamps, and we got about 2000 and a little bit out of it before it hit 1.2 volts. So that's only 2/3 of its rated current. So yeah, and truthfully, a lot of equipment, once you're down in that region between these two dotted lines, it's marginal as to whether your equipment will be working or not. So this battery lasted somewhere between, let's say, 4 hours and 8 hours. The Energizer lasted somewhere between 12 hours and 13 hours. So 5 hours longer in total. So yeah, so straight away there we see an interesting comparison. Now let's put this in context a little bit though, because the nice power costs half of what the Energizer does, and this is a constant high current draw. This doesn't necessarily hold true if, for example, we've got something we use for 15 minutes and we switch it off for a day, then we turn it on for 15 minutes again, an alarm clock or something like that that's got very, very low current draw. They're likely to be a lot closer in that instance, and you know, there's a lot of space for recovery of voltage and things like that. So in those circumstances, for low power, then this nice power might be absolutely fine, perhaps delivering 80% of what the Energizer will deliver. So 80%, but it costs only 50%, so actually that's a good deal. Just don't expect to get what it says on the tin out of it, that's all. But yeah, so for that it will be value. For higher things like my little radio transmitter that's using for my microphone, then yeah, it's rubbish, pointless. So you could argue that, okay, well, you know, it's only 5 hours, so you know, the Energizer lasts twice as long but it costs twice as much, so really they cost the same. But they don't cost the same because the environmental damage is the same on both of them, but I need twice as many of the nice powers. So, you know, Energizer is definitely better for the environment and better for my pocket in that instance. So let's switch to chart 2. So this is essentially accumulated power, or the total power that's being delivered by the battery over time. So this top slope here is again, this is actually a slight curve. It's not really a straight line, it just looks like it on the graph. So this is the power, and it's been taken in slices averaged over every 15 minutes that the Energizer has delivered, and it's the top line. So we see actually, because the voltage coming out of the nice day is a little bit lower, the current is the same on them both, the nice day is actually delivering less power, and at the point that the nice day runs out, side by side it would have delivered 12% less power than the Energizer. So what does that mean in practical terms? Well, if you've got a torch it's 12% less bright. You know, so for many things it doesn't really matter. You're not really after the power per se, you just want enough current and enough voltage, and in truth any extra power that's coming through is getting pissed away in resistors and things like that. But yeah, okay, but let's have a look at the total sum at the end. So because this is horizontal here, because of course the nice power has stopped working at this point, so it doesn't deliver any more power, and the Energizer continues, and in total it delivers 42% more power than the nice power, or the nice power is 42% lower than the Energizer. So so there we go. Yeah, so if I was putting these in a torch, I'd definitely be putting the Energizer in, and I wouldn't go anywhere near a nice power for that. Okay, so there's the graphs and the data. Does that leave us? Essentially, in low power things, the nice power might be okay, but in truth, you may as well just buy normal alkaline batteries for that circumstance. They perform nearly as well, unless you plan to use them outside in freezing cold weather. I'll be buying some lithiums from Energizer because I do need some high power batteries, and I need them to work as advertised. So that's my choice. I will of course be using a battery bank now for my radio microphone and things like that, and I'll be doing this completely separate review. So anyway, I hope you've learned something. It's been a slightly longer video than planned, but if you liked it, please give it a thumbs up. If you haven't already done so, please subscribe. Of course, you can put comments in the section below, and I'll put plenty of links in to all that information from Energizer and to the products as well. See you soon. Take care.